Everybody. So this is a super important topic relating to the moment of inertia. So if you're given some shape, let's pick one of these, here, a thin rod. So like a stick, or you have a stick. The moment of inertia about an axis right here in the middle is right here. Thin rod about axis perpendicular to the length, and then right in the middle, 1/12 ml squared. So here about the center of mass, 1/12 ml squared for mass m, length l. So here's the thing. What if it's not rotating about the center? What if it's rotating about over here? For example, like you have a pendulum where it's a stick kind of going back and forth like this. And we want to know the moment of inertia about the end, not the middle. And it's different. It's different. Around the end, it's going to be different. And definitely more. It's going to be greater than the moment of inertia about the center of mass. In fact, the moment of inertia for any object about an axis going through its center of mass is a minimum. So remember that forever. Right? The moment of inertia through the center of mass is a minimum. If you rotate anywhere else away from the center of mass, for example, right here, I'll just call this point A, it's definitely more. And then as we move farther away from the center, even more. So then over here, even more than over here. So this is a minimum. Over here, even more. Over here, even more. Okay, how much more? Let's talk about that. How much more? So this is definitely more than this. How much more? It is about the center of mass plus extra. How much extra? The mass of the object times the distance between these two axes squared. And the axes have to be parallel. So for example, like straight out of the page over here, straight out of the page over here. They can't be misaligned. They have to be parallel axes. And so this is called the parallel axis theorem. So for this particular example, how far is this? L over 2. L over 2 squared. Okay, so if we just plug in the numbers, the moment of inertia about the end, right? So this is 1/12 ml squared plus, and so that's L squared over 4. So 1/12 plus 1/4 is 3/12, 4/12. 1/3. Okay, so about the center, 1/12 ml squared. About the end, 1/3 ml squared. More, 4 times more. Okay, let's pick another example. Let's say I have over here point A, which is, let's say, L over 4. So what's the moment of inertia about point A? I guarantee you it's more than the center of mass plus extra. How much extra? The mass of the bar times the distance between the two parallel axes squared. Okay, and when you do the parallel axis theorem, it's always the center of mass and somewhere else. Not, for example, like going from A to the end. It's always from somewhere to the center of mass, or the center of mass to somewhere. Okay, let's try maybe a more complicated example. Let's say there is a bar like this, slender bar, and then we know the mass m, length L. Okay, and then let's say we release this from rest. So it's at rest, and it swings like this. And now I want to know, what's the angular velocity here? Okay, so how do we do this? So let's say there's no friction in this hinge. So this is conservation of energy. Initial, final. There's no friction, so there's no work being done by friction. Okay, how much kinetic energy? It's at rest. So kinetic energy is 0 over here. How much gravitational potential energy? Depends where we pick the datum. And how do you compute gravitational potential energy with respect to the center of mass of the bar? So it's over there. Then afterwards, it's over here. So where would you like to pick the datum? Totally up to you. You can pick it here. You can pick it here. Here. There's no wrong choice. So how about we pick the datum right here? Okay, so it doesn't have any kinetic energy because it's at rest. It's at the datum, so there's no gravitational potential energy. So we're done here. Okay, so now, final. Gravitational potential energy. We're now below the datum by this much. So it's negative mg all over 2. How about kinetic energy? Kinetic energy is 1/2 I omega squared. But what is I? That's the moment of inertia about over here where it's rotating, about the hinge. So in this example, it's a bar rotating about the end, which we solved that earlier over here, like this. Right? But let me rewrite it. So about the end, I'll say about the hinge, right? About the hinge is about the center of mass plus extra. How much extra? The mass of the bar, the distance between the two parallel axes, squared. And about the center of mass, we just get straight from the appendix, from that table, 1/12 ml squared. Okay. So then there's only the one unknown to solve here. So let's put everything together. So I'll move this on the other side of the equation. 1/2, and then I was 1/3 ml squared, omega squared. So move all this in the denominator over here, and then we have omega. Okay. So that's one way to, well, maybe I should just finish writing this. Okay, let's multiply both sides by 2 m, and then the 3 goes on this side. 3gl over L squared, so L over L squared is like this, equals omega squared. So here we go. Okay, now let me copy this picture. There's another way to interpret the kinetic energy, because here we considered it's rotating about the hinge. Another way to interpret it is it's like the center of mass translated like this. It was going along this path, so the center of mass is translating. And also, it's like the bar was rotating about its own center of mass. Right? The bar was like this, and then it's rotating counterclockwise, and then ends up this way. So it's like the center of mass is translating from here to here. Simultaneously, the bar is rotating about its own center of mass. counterclockwise. So the two things are happening at the same time. Translation plus rotation. So then, let's say we pick the same gravitational potential energy, 0, and then on this side, minus mg L over 2. But for kinetic energy, the center of mass is translating, and so it has velocity like this. So what's the kinetic energy for the center of mass? 1/2 mv squared, where this is the velocity of the center of mass, translating. So this is translation. Plus, the bar is rotating about its own center. 1/2 I omega squared, where this is the moment of inertia of the bar about its own center. Okay, which is 1/12 ml squared. So now if we put all this together, let me move this on the other side. 1/2 mv squared plus 1/2, and then 1/12, so 1 over 24 ml squared omega squared. Okay, and we want to solve for omega, but then what's up with this, right? So what's the relationship between this and this? And if it sounds familiar, r omega. And what is this radius for this particular example? L over 2. Okay, so I'll just write L over 2. So we can substitute this here. So let me do that. So that squared, L squared over 4 omega squared. Okay, so things cancel, mass cancels everywhere. And then here we have, let's see, let's multiply everything by 2. So let's do this carefully. So L squared over 4 omega squared, 1 over 12, L squared omega squared. Okay, and let's divide everything by L squared. Okay, let me just clean this up. Okay, and 1/4 plus 1/12 is 1/3, which we can move on this side. So omega squared is like that. Let's compare that to what we got earlier. Same, right? Okay, so two different ways to think about that kinetic energy. It's like either rotating about the end, or it's a combination of translation and rotation. Okay, so let me know if you have other questions about this. Maybe it takes time for it to sink in, and I'll see you in the next video.